So when we finished up yesterday, we had our equations of motion. And that was omega final was equal to omega initial plus our angular acceleration times time. Omega final squared is equal to omega initial squared plus 1 or 2 times my change in angle. And we had my change in angle was equal to my initial times time plus 1/2 our angular acceleration times time squared. So we had those items. So, and we did a problem looking at a wheel going around a circle. So we'll just do another one. So we're going to use a constant angular acceleration of 2.5 radians per second squared. We're going to start out with an initial angular velocity of 1.5 radians per second. We're going to start at our initial angle is going to equal 0. We want to find our change in angle from t is equal to 0 to t is equal to 1.5 seconds. We want to find our angular velocity at t is equal to 3 seconds. And we'll work this problem like we've worked them before. So we know we've got our change in angle. So our change in angle is going to equal our initial times time plus 1/2 our angular acceleration times time squared. We started out at 1.5 radians per second. Our time is going to be 1.5 seconds. And our angular acceleration is 2.5 radians per second squared. And our time is 1.5 seconds squared. So we can calculate that change. That gives me 2.25 radians. This gives me 2.81 radians. We'll try that again. Make sure I did it right. Yep. So my total here was 5.06 radians, but because we don't think well in radians, we want to know this in degrees. So if I have 5.06 radians, and we know that there are 360 degrees in 2 pi radians, we progress 290 degrees. We can calculate our final angular velocity. It's going to be equal to our initial angular velocity plus our angular acceleration. So we started at 1.5 radians per second. And we had our constant angular acceleration of 2.5 radians per second squared times our we wanted to do it for 3 seconds, so that's 3 seconds. Get our 2.5 times 3 plus 1.5. We're going to end up at 9 radians per second. So we can work those same kinds of problems that we had before. One of the things that we had talked about at the very end of class yesterday is I can give you an angular velocity in terms of cycles per second or in like revolutions per minute. So let's think of a 45 RPM record. And we want to calculate our angular velocity in radians per second. 1 revolution is equal to 2 pi radians. So 45 revolutions per minute. We want to be in radians per second. We're going to calculate our 45 revolutions per minute. There are 2 pi radians per revolution. For 1 minute, there are 60 seconds, and this will give us our radians per second. And I'm going to get 4.71 radians per second. But I wanted you all to see the fact that we can rewrite those items. If I give you something that is in radians or revolutions per minute or something like that, we can actually calculate our angular velocity. Okay, now hopefully you all watched that one video. So if I have a curve here and we start out with a constant linear velocity, and we can go back and forth between our linear and our other ones, because we saw that our change in angle is equal to our linear distance divided by r. So I can do r theta is going to give me s. We can do r omega, which will give me my velocity, and r alpha is going to give me my tangential, and this is my tangential acceleration. Because we will get in, even if I'm going at a constant linear velocity or a constant speed, I am going to get an acceleration, because remember, vectors have direction and magnitude. So we're going to end up with an acceleration component that's tangential to our curve, and we're going to end up with an acceleration that we call our centripetal acceleration, which is our center-seeking acceleration. And that's our centripetal acceleration that's causing us to pull into the circle. And it's coming from the fact that I'm going to be going around this circle. This gives rise to a couple of things, because remember, we actually talked about this a while ago. We had Kepler's laws. And one of Kepler's laws was, if I look at my period here, we had our areas of our triangle, but we also had that the period squared was roughly proportional to the radius cubed. And this gets us into this idea that if I know how fast I'm going around my circle, I can get a centripetal acceleration of v squared over r. And this gives us what we feel as we're going around a curve in a clover leaf or something along those lines. So my acceleration total is going to be related to the two components, my centripetal acceleration plus my tangential acceleration squared, because we've got a vector that's pulling things in. So I really encourage you to go look at those videos where they're demonstrating it and they're actually drawing those circles in there, because it's a heck of a lot better than my scratchy drawing on a piece of paper. So we can look at our force is going to be our mass times our acceleration, and we can look at a centripetal acceleration in terms of an equation that looks like that. One of the other things that we talked about that comes back to play is our force due to gravity. Newton's law of universal motion. And that gets us back into these items as well. So you do have that in our particular chapter that we want to look at. So just a reminder, we've actually done problems like this before, bringing in how these things come together. And I'm double checking. Okay. So you've got those problems as well. Now, one thing that we want to look at is our angular velocity does have a direction. And this comes from our right-hand rule. So if I'm going to use my right hand, I'm going to go in and my angular velocity is going to come out of my paper. So you're going to have, if I'm going around this direction, my angular velocity is going to be coming out of the paper, and it's going to follow the right-hand rule. This will become important when we get to torque, because we all know that if I have an object, and we'll get to torque tomorrow, so if I have my wrench, and I'm bringing my wrench and I apply a force here, this is going to cause the bolt to move in that direction, and my bolt is going to come out of my page, and it's all coming back from the fact that I have this angular velocity, which is going to allow me to come up out of the page. So we will see that as we go into the next chapter. Okay. I think what we will do is let's do one of these. We got a problem here. Let's do a problem. We've got a car traveling around a turn. With a radius of 30 meters. And we're traveling with a speed of 5 meters per second. We want to calculate the centripetal acceleration. So our centripetal acceleration is going to be AC V squared over R. We're going to have our V squared as 5 meters per second squared divided by our 30 meters. We're going to get meters squared, seconds squared divided by meters, which is going to give us meters per second squared. So our units are going to work out. That's going to work out really well. This is going to give us 25 divided by 30, and we're going to get a centripetal acceleration of 8.3 meters per second squared. So we're going to use this car. We've got a car that the car is going to enter a turn that has a radius of 30 meters. So we're going to use the same radius. We're going to accelerate from 5 meters per second to 7.5 meters per second in 2 seconds. We want to calculate our tangential acceleration, our centripetal acceleration, and our angular velocity. Our tangential acceleration is just going to be our change in velocity over our change in time. So we're getting our 7.5 minus 5 divided by the 2 seconds. And I've got meters per second divided by seconds. This is going to give me 1.25 meters per second squared. Our centripetal acceleration, now that we're at our 7.5, it's going to be 7.5 squared divided by 30. It's going to give me 1.875, and that's in meters per second squared. Our angular velocity after we reach our 7.5 is going to be our 7.5 divided by 30. Gives me 0.25 meters per second. But my new acceleration total is going to be my centripetal acceleration squared plus my tangential acceleration squared. And that's going to be my 1.25 squared plus my 1.875 squared. And we're going to take the square root of that. And that's going to give me 2.25 meters per second squared. So that gives you a different one to kind of look at, a different way of looking at a problem. All right. That gets us through chapter 7. We will do chapter 8 tomorrow. Then you will have time for your test on Thursday. We do chapter 9 on Monday. And then it's finishing up stuff. Question.